We will present AiSCREAM, Absolute Target Localization with Language-Conditioned Cross-View Alignment for Autonomous Vehicles. We study how an autonomous personal mobility system can interpret a language instruction into an executable metric goal. The global personal mobility devices market is projected to reach $20.1 billion by 2033, highlighting the growing importance of personal mobility. For autonomous mobility systems, a key requirement is intuitive interaction. Users should be able to specify a stopping point through language, just as they would in a taxi. For example, stop behind the bicycle. We formulate this problem as referring navigable position localization, or RNPL. Given a navigation instruction and a single front camera image, the model predicts a target position and an acceptable region in an egocentric coordinate system. We represent the output as x, y, and r, where x and y denote the metric target coordinates, and r denotes the radius of the acceptable region. This task has two main challenges. First, the model must ground the instruction in the visual scene and understand spatial relations such as next to or behind. Second, it must estimate an absolute position in meters from a single monocular image, where depth and geometric information are limited. Our key idea is to synthesize an aerial semantic view, or AIS view, from the front image. Unlike a metrically projected bird's-eye view, the AIS view is generated in the image domain. It therefore preserves appearance-level scene characteristics and provides stronger semantic correspondences with the front image. AiSCREAM consists of two main modules, the AIS Cross-View Representation Alignment Module, or ARAM, and the Multitask Absolute Position Localizer, or MTAPL. ARAM first extracts language-conditioned semantic masks from both the front and AIS images using cross-view consistent semantic segmentation. The images and their masks are then encoded with shared image encoders. Bidirectional cross-attention first fuses appearance and structural cues within each view, and then aligns the two views. The resulting representation jointly captures fine-grained semantics and egocentric geometry. MTAPL combines the cross-view representation with the instruction embedding and predicts three complementary outputs: the target region in the front view, the target region in the AIS view, and the absolute metric target. It then projects the initial metric prediction onto the front image. We also introduce a height-based cross-view loss. It supervises the absolute and AIS view predictions and penalizes target regions that overlap with obstacle masks, encouraging physically valid predictions in navigable areas. The MLLM Reshape Localizer receives this visual prompt together with the numerical prediction, evaluates whether it is physically and contextually plausible, and corrects implausible outputs. We evaluate AiSCREAM on the single-target subset of GRIN drive and on our newly constructed Dramatist benchmark. Together, they contain more than 16,000 instruction image pairs and cover diverse road layouts, traffic systems, and visual conditions. Here is a quantitative comparison of AiSCREAM and baseline methods. AiSCREAM achieves the best RMSE on both benchmarks. On GRIN drive, it reduces RMSE from 10.51 meters for the strongest baseline to 4.72 meters. Under the same single image setting, human participants obtained RMSE value of 7.45. AiSCREAM therefore achieves lower localization error than human participants. Ablation studies further confirm the contributions of both the AIS view and cross-view consistent semantic segmentation. The qualitative results show that baseline methods often identify the correct landmark but place the target on the wrong side, outside the road, or inside an obstacle region. In contrast, AiSCREAM better preserves the instructed spatial relation and predicts the target within the drivable area. Additionally, here are other qualitative results of AiSCREAM. As shown here, our method produces appropriate predictions even under challenging conditions, such as dark scenes and adverse weather. It also performs consistently across diverse environments spanning Tokyo, the United States, and Singapore. In summary, AiSCREAM combines language-conditioned cross-view alignment, obstacle-aware supervision, and prediction-conditioned MLLM refinement. It substantially improves metric target localization from a single front image and provides executable goals for language-guided autonomous mobility. Thank you.